Good day, everyone. Welcome to my presentation of WCCI 2020 in IJCNN session. So my name is Dai Hoang Tran. I come from Vietnam, and I currently doing my PhD degree at Macquarie University, Sydney, Australia. And my research interest is recommender system, as you can get from the paper title. Now, before I start presenting my work, I would like to express my gratitude on the hardworking staffs, members, and organizers of WCCI who, amid the COVID-19 situation, still managed to provide us, the researcher, a healthy platform to communicate and exchange our ideas, our research outputs. And to the audience, I thank you all for tuning in and listen to my work. I hope you gain something useful out of it. Now, let's begin. Now, the paper title is HeteGraph, a convolutional framework for graph learning in recommender system. So in this work, I apply convolutional neural network techniques in graph learning for recommender systems. And as you can see, I am the first author. Quang Xiang is my professors. Wei Ma Zhang and Nguyen Le Đăng Khoa are my supervisors. Abdul Wahab and Monaza are my lab mates, and Nguyen Tran is my senior mentor. So let's go to the contents. So here are the contents of this talk. First, I introduce about the recommender system and then talk about the next advancement of it, which is graph recommendations. And then we identify the problems that exist within graph recommendation techniques. And then we propose a novel approach called HeteGraph based on graph convolutional neural network architecture. And then we talk about the applications based on HeteGraph platforms. And finally, we conclude our work. Let's do the introduction now. One, introduction. So what a recommender system? Recommender system are the engine born by the internet. They don't exist before that. With the booming of online services, we are surrounded by millions of things that are of interest, from news to online shopping items to social media, etc. So the need to have a personalization for each person increased tremendously, and that's the reason why recommender system were born. In a nutshell, what it does is that it will learn user preferences and recommend relevant item to each person. Now today, recommender system plays a major part in modern technology services. As you can see from the slides, we have Facebook, we have YouTube, the biggest sharing online video, we have Amazon Books, we have Netflix movies. So those are very successful online services that utilize recommender system. Some of the interest scenarios that you can find with a recommender system is when you want to find an items of interest. If you read books, you might want to find similar book that meet your taste. If you are traveling and you want to explore new area, you might want to check for recommender system that recommend you which place to go. The benefits, now with the practicality of a recommender system, the benefits are tremendous. If you have a good recommender system, your service will engage more users, which in turn return more profits to the providers, and it also can help to reduce user cognitive load in the current works of big data. So how do we go about an approach to design a recommender system? So there are two approaches to design a recommender system. First one is content-based filtering, and the second one is collaborative filtering. For content-based filtering, this is very intuitive. If you look at this picture, each user reads this article and the system just finds similar articles with similar content to the one that the user had read. And that is the principle of a content-based filtering method. So for this, any machine learning method that used to learn the similarity between attributes of item can be used, and it is especially used a lot for news recommendation. The second approach is collaborative filtering. In contrast to the first method, this collaborative filtering approach doesn't need to know the content of the items. What it does is that if two users have similar preferences, such as they both read the same articles, so the system assumes that these two users have similar tastes and they can recommend the items of one user to the other one. And the most common method to approach this collaborative filtering was KNN and metric factorization. And here is an example of how metric factorization work. If you have a user item rating matrix with missing elements, you can use machine learning methods to factor them into two smaller latent matrices. And when you multiply them together, you reconstruct a similar rating matrix with all of the missing element filled in, and then you can use those to do the prediction. Now, graph approaches is another way to design a recommender system. As you can see, usually the data of a recommender system involves a user, an item, and the interaction between them. So if we can represent the user as a node as well as the item and the interactions is the edge, then we have a graph structure data. Also notice that we can also attach attributes to node and edge. And that's why if we can leverage graph the structure data in recommender system, we have a hybrid approach where we can leverage both the content and the interactions between user and items. And the best part is we can leverage deep learning neural network algorithms for this graph approach. Here is the typical process in leveraging graph approach for recommender system. From the raw data, we construct a graph structure and then we try to embed them into an embedding space, and then we feed that embedding into a neural network model to learn the final embedding before we can do the recommendation process to the user. As I discussed before, to learn graph embeddings space from the graph structure data, we need to have a method to do that, and graph convolutional network, in short GCN, is the most recent approach that has gained a lot of attention lately. And basically it is a deep neural approach to solve graph applications. It can be used on homogeneous graph applications such as document classification. So homogeneous graph is the type of graph that all the nodes are the same type. For example, in this image, all the nodes are the same document type. Or it can be used in recommender system, which is a heterogeneous graph type. What it means is that in the graph we have multiple node types. And this is a simple form of GCN taken by the reference 1. This is the mathematical formula of a GCN. We have the usual variable of a deep neural network. So this is sigma nonlinear activations. L is the different layer in the neural network. H is the feature matrix. And W is the weight matrix. Pay attention to this adjacency matrix. As you can see, adjacency matrix is applied to all the layer within this GCN. So because it keep being used throughout on different layers, it become a local filter, and that's why it has the name convolutional in this graph, in this method. Two programs. So the GCN method, even though it has gained a lot of attention lately, there are several problems that we need to address using GCN. First is that it requires full adjacency matrix during the calculation, as you can see in the mathematical formula before, and this become invisible in large graph. If you have million of nodes and million of edge, then the adjacency matrix becomes so huge that it's become intractable to do the calculation. And secondly, that GCN method is designed for learning in a transitive setting. That means it's only remember the current graph, so it kind of static. And if you have a dynamic graph, that means your adjacency matrix keep changing. That the reason why it is not generalized to a new node. And finally, how do we extend GCN into heterogeneous system as in a recommended system where we have different node type and different each node type have its own attributes. So we want to address one of these challenges, and that's why we propose our novel approach called HeteGraph. The contributions of this novel framework is as follows. First, it solves problem 1 and 2 by extending the work of graph search using node neighborhood sampling and aggregation convolutional operation. Secondly, it solves problem 3 by using suitable embedding strategies to map different node types into the same embedding space to allow the heterogeneous system to work. And finally, we provide proof of concept recommended system application for top K and diversified recommendations. This is the overview of our HeteGraph framework. Our framework has 4 different phases as denoted here. In phase 1, we do the neighborhood sampling, and in phase 2, we do the convolutional operation on both the node and its neighborhood to find the representation of the node itself. In phase 3, we use different embedding techniques to map them into the embedding space, which will be used in phase 4 as our application model. Now, phase 1 in conjunction with phase 2 and 3 help us to solve the problem 1, 2 and 3. And phase 4 help us to realize our HeteGraph potential. So let's look at each phase in detail. Phase 1, node neighborhood sampling. This figure illustrates our approach to the node neighborhood sampling. As you can see that instead of using a full adjacency matrix as a convolutional filter, we use node neighborhoods and edge weight bias to walk through the graph to form a local neighborhood graph to do the convolutional operation. And due to the heterogeneous setting, we use a two-hop sampling method to reach nodes of the same type. For example, as you can see on the image, if you have a user node and it has an interaction with an item, then the next hop will be another user, and that's why we use two-hop sampling to sample similar user as well as sample similar items in this setting. And also we bias the work beyond the weight bias of the edge. If the edge interaction has a higher weight, we will give it higher probability to be sampled during the sampling phase. And for each node, we will sample multiple paths, and these path attributes in conjunction with the node attributes will be used in the convolutional operations. Phase 2 and 3, convolution and embeddings. So after the sampling process of phase 1, on phase 2, we extract each node attribute here, and we also extract each node neighborhood attribute here. So this is a vector and this is a matrix. So to make it become a vector, we do a max pooling aggregation to squat it out to become a vector, and then we concatenate these two vectors together and run them through a non-linear activation to learn the representations. And this is a user node. We do the same for item nodes. That is the phase 2 convolutional operations. In phase 3, for the embedded phase, depend on the type of application, we do different embedding techniques. Either we keep them the same we just run them through another nonlinear activation, or we concatenate them together depending on the application models. And as I mentioned earlier, these three phases 1, 2 and 3 really help us to remove the problem 1, 2 and 3 as well. So now let's move to the final phase, phase 4 application, where we derive two different applications from our HeteGraph platform. The first application of our HeteGraph framework is top K recommendations. So in this scenario, a user will get recommended by 5 or 10 items based on his interest. And the way we handle the trainings is as follows. First, we try to concatenate both user and item embedding into one long vector. So this is called the edge embedding between a user and item, and then we let them go through a multi-layer perceptron network to train. So the final output is the true rating, and then we just back propagation through the whole network to train the weight. And that is how we handle the first application. Now let's look at how this application 1 works in compared to other techniques. And this is the evaluation of our first app. As you can see, we use two different datasets. First is movie lens, and second one is book crossing. So they are two popular datasets in the research community of recommender system. And we use four different metrics to measure the first app. First is root mean square error, and the second one is mean absolute errors. And then we have the precision at 20 as well as recon at 20. For the actual measurements, we derive two different models to compare with other popular techniques. So HeteGraph supervised is the multi-layer perceptron network that I just explained. And the second one, HeteGraph mix, is another model that I use a different embedding technique, which I do not put it here on the slides. Anyway, they both achieve a reasonable top K prediction score, as you can see on the table, across two datasets. So we confirm that our HeteGraph framework works well with the most common scenarios for a recommender system. Now let's look at another popular applications, which is diversified recommendations. A typical example of this type of recommendation is when you do traveling. You don't want to keep visiting similar places, such as keep going to the beach, keep going to the museum. You want to explore a variety of different places. And in this approach, we use a different embedding strategy. We don't concatenate the user embedding and the item embedding. Instead, we use their own representation and we find them in the embedding space. Now, if two users are close in the embedding space, we assume that they have similar preferences. And when we come back to the original graph, these two users might stay far away even though they have similar preference. And in that sense, if the items of user B are recommended to user A, the chance that this item will be very different to the one that user A is similar with. In terms of the evaluation for our application 2, we achieve state-of-the-art results on both datasets for the diversity score. And the diversity score that we use is the ILS, which is defined as here. This is the summation of similarity between an item pairs for all the items in the dataset and divide by 2 times the amount of data. Now that we have gone through all the phases of our HeteGraph framework, here are the conclusions. So in this work, we propose a novel framework called HeteGraph that is able to handle heterogeneous graph structure data using graph convolutional neural techniques based on local neighborhood sampling, and we're able to derive two popular recommendation applications out of it. For the future work, we plan to improve our model in terms of accuracy measurements. We want to compare it with more techniques, and as well as we want to improve our sampling technique to account for more edge attributes. Here are the references that I use in these presentations. And this is the end of my talk. Thank you for listening. Here are some handy information in case you want to reach out to me or to our lab or learning more about Macquarie University. Thank you.